I couldn't help but keep focusing on one particular aspect of this structure. So you're talking about how we got a cosmological model now, which happens to be at its largest scales, much, much larger than the universe we're aware of so far, right? But it's finite. And we're claiming the simplest possible geometric self-balanced structure that you can have. Okay, it's based on the minimum 3 manifold, and then externally the n hypersphere of maximal volume. Well, that means that we end up with a 2-dimensional surface on the very outside, maintained at first step on the inside with a 4-dimensional surface. Right? It goes from 2-dimensional to 4-dimensional. But what does that mean when things are going through the middle? When things are coming out from the inside in this cycle, if you think of it like a vortex, okay? That means that the things that come out have an upside and a downside. And when they come back in here, they're inside out. Right? Mm-hmm. Okay. And you said here there's a cycle that they go through, but the last part of the cycle is black holes, right? So if you think a black hole goes in, or a boundary of a black hole, but it comes out an inside-out boundary of a black hole, okay? So a black hole has its boundary where it all focused towards some center. But the inside-out boundaries of a black hole, no one has an idea what that is. But we're claiming here in the model, it always inverts this way. This whole collection of possible boundaries here are exactly the inside-out boundaries. All the boundaries of matter are the inside-out boundaries of a black hole. I don't know if that made sense. It's a little bit new way of structuring a sentence for that, or new way of talking about it. But I hope it makes sense. So the surface comes out, and it has to be exactly inside out each time as it goes through the center.
It's funny because one of my other friends, colleague, she's been saying this for a while now, and I really haven't understood what she meant by that. And now I'm like, all right, well, Thad's telling me basically the same thing. It's just our conceptualization. That's why I'm like, I think we're all kind of heading in the same direction.
What did she say?
She basically is saying it's more of a one-sided surface, but basically you're still seeing that inversion effect.
Because it's a Mobius. She's
right. Right, okay.
So what you're kind of saying is that the entire universe is the opposite of a black hole.
No, it's both a black hole and its opposite, put into balance. It's you create a boundary called a black hole and exactly the opposite boundary, whatever the image is, right? But you put them actively engaged with each other, forming another boundary that's closed. You make that closure be the boundary of the minimum possible manifold. So now you've got a system who's using its own parts over and over and over. It's actively wanting to go there, and other parts actively want to go there to fill in where you're going, and everything's closing perfectly, right? So you can look at the boundaries from the outside of the positive curvature and think of them as, say, a black hole boundary, or you can be looking at the boundaries from the inside of the curvature and be now looking at the boundaries of matter. So all zeros are double-sided. Okay, the zero is a division boundary, the limit of division, right? It's how you break up the things that are dividing things. The zero determines that in the system. So zeros in a balanced construction or in a mathematically balanced arena, okay, the zero always defines a boundary, and it's always double-sided. So you can think of the universe you're aware of as half of the story, and inside of that, or outside of that, it would depend on which one you want to see yourself at. Are you on the inside or the outside? But on the other side is the story of the black hole surfaces. The zero boundaries still, okay? So all zero boundaries are double-sided. Division boundaries being held up by something. All hurricanes have wind speeds on one side colliding with wind speeds on another side. They're double-sided. Okay. Anyway, that's why my mind went off on that when you were talking about this. But this is a cosmological model that's extremely satisfying because you can specify and stipulate every single geometric structure through the scales that exists. It's finite, first of all, right? And it forms all the way to a balanced projection of one sphere. Very easy so far to understand. But notice, if you're in the universe before you have anything like this, and it's just random noise, so somehow there's an infinite randomness around, then to form this, or in that region of randomness, there's no coherent meaning to scale of any kind. Time, space, charge, mass, temperature, they don't mean anything. A scale, the second, doesn't mean anything. The meter doesn't mean anything if you're in a universe that's completely infinite random noise. There's no meaningful structure built in. Scales don't exist until a minimal universe exists, and its pieces that make it up, the different size pieces that make that minimal universe up, at the same time working together to find different scales by which you can now make meaningful measure. And all those scales are born together. You go from no meaningful measurements, no scales in existence, to a minimal constructible universe that comes with minimal scales, dimensions, and size. Not that there's a certain number of different kinds of dimensions, not just a number of kinds, but you have different sizes assigned, a scale associated to each one. That's important, right? If you have a minimal construction, that's what's going to happen. There's going to be an actual size for each of the different kinds, not a fuzzy conceptual size. It's an actual size. So scaling is important, but it's important in two reasons. Not just because it gives you scales to make measures, but conceptually it gives you bases of measure. Things that can be measured. That's the point. So things that can be measured are reported via numbers too, as long as you're reporting in those bases. Those numbers are actually inscriptions of a balance in the system, a particular balance. Each number refers to a particular balance in the structure, right? Okay, so our cosmological picture here is that we have the minimal possible geometrically self-balanced. So there's no magic being induced in the system. There's nothing that it's leaving out or requiring to have injected in to keep itself going, right? So it's just self-closed system. And we're going to call that a minimal universe or constructible universe. And the geometric story, as you go from the biggest sphere all the way down to the smallest wrapped complement volume, the hyperbolic figure eight knot on the inside, it changes a lot through the scales, but well, I should be more specific. It changes a lot through the smaller scales until we get out to the 10 to the negative 8. And at that point, it's a torus, okay, a donut shape that's inside the big sphere that's the whole projection. The outer sphere has for its most primary experience on the large scales, all of its division happens because there's a torus, hurricane torus of space, keeping its balance. That's the boundary that the rest of the sphere is resting on. That's why it can exist, okay? So that toroidal decomposition, the fluid of this balance itself being decomposed under a toroidal bound, gives us exactly, when we zoom in, we get a torus, but in the division boundary of this torus goes like this. Right? If you think you're a piece of fluid, you're going to be moving around, follow wherever the fluid makes you go from where you started. But if you track all the fluid motions, nobody crosses these boundaries. That's the region where nothing crosses. If you're close to it, you're going right along it, not going through it. Okay, so there's a division in the structure, not with a gap. It doesn't introduce a gap, notice, right? It's just a cutoff zone where all the medium itself divides around, doesn't cross through. Okay, so it's a little higher order concept in geometry because it's not an edge of a circle. It's an internal boundary that's there over time. It reveals itself over time. Once you're aware of it, you can paint it in and just watch every step at time and verify, yep, nothing's crossing. But you have to watch for a little bit to notice, hey, look, you notice here that all the stuff's active over here, but it never crosses this way, here. It might be active there, but it's always in a certain direction, right? Okay, so there's an internal boundary being maintained by these boundaries, by that hurricane wall. These are the ones you can see, right? If you were nearby, you would be looking and be blatantly aware that these boundaries are there. Okay, there's a zero boundary there, but that zero boundary comes with an opposite kind of zero boundary. Cool? Okay, this is the internal first step decomposition of the outer sphere made that's ultimately internally resting on the minimal complement volume, the hyperbolic figure eight knot.
Could you say that last part on the left one more time?
The whole part?
Just basically as it crosses over. The crossover part.
Oh, so there's a big sphere resting on top of this decomposition, but these lines that I'm drawing, this is a two-dimensional surface, right? It goes around here. And this is a different two-dimensional surface here. Both of those surfaces are called into existence at the same time by this balance, okay? So this is a different kind of looking wall than this, but whenever you make this wall, this is necessarily in between it. It's the walls are, if you color all the little dots in the fluid and then track to where they went, okay? Keep the same colors, you can see where each color moves. But you would notice that the paths that all the dots followed never crossed this exact line, right? In fact, the closer they got to that line, it was very systematic and evenly, smoothly doing this. As they get closer to this line, they're going more and more and more and more exactly along it. They can be going exactly along it as they approach it. As you get out here, you can be doing all kinds of different motions, but you get in there and it's moved exactly along it.
So it's a limit of the degrees of freedom.
Yeah. It's a zero etched into reality, and that zero is a no-go zone. You don't get to cross it. Zeros are all double-sided though, so in order to etch it in, you had to carve in. Right? Here's the other side of that zero. They come together. Follow? Is it?
It's kind of a leap, but it almost reminds me of the jets that are coming out of a black hole.
Yeah. It's not much of a leap. It's the same sort of thing we're talking about. Now, you can have different angles for your cone-on-cone structure, and we're going to call all of those hyperbolic decompositions, because what changes that? Just the size difference of the torus circles compared to each other. Right? Those are all allowed, and they're all decomposing into tori on cone-on-cone. Okay. Next step is to just zoom in closer at this two-dimensional surface. This one's a smooth bound. When you zoom in closer to it, still looks pretty smooth. But this one, it resolves into a whole bunch of other, well, shoot, I need to actually draw them as tori that go around the center. Like this. And so on. Okay? So they're all linked into this one two-dimensional surface. That's what you see from the distance. But when you get close to the surface, you notice, oh, it's actually a much more rich two-dimensional surface. It breaks into another structure that's composed of all these other tori. Different scaled and a fixed whole number collection of different tori inside the torus. Okay? Each torus to torus transition through the scales takes advantage of the exact same structure of cone on cone, rotating everything about. So when you're partitioning the domain into smaller and smaller torus as you go in, it's always dividing a section that rotates like this, introducing a cone on cone. You know what the torus was, right? And cutting up the domain that way. So it's a fractal decomposition of tori that we're really talking about. But when we're saying that, we're also meaning the cone-on-cone boundary that you're introducing each time as you go in. Okay. How does this help other than giving us a richer, specific set of details for a minimal cage, a minimal universe? Well, it helps because it turns out that the properties of this minimal universe, the geometric scalings for this hyperbolic construction and so on that fit to the hyperbolic figure eight knot, those scalings and all those properties of intersections from these different scalings that put into this one set give us all the properties of physics and chemistry. That's the really big deal. Now, we didn't get that story going forward. We got that story going backward. right? We looked at all the properties of physics and chemistry, the literal constants of nature, right? And the composite constants of nature, so how the constants are used together to do things, right? So the next level up, and I call those the chemistry constants. So all of these constants, which technically once we add the chemistry composite ones, we have 8 times more data points than just the base 44 for physics. So that's a lot more data points, and we're almost done wrapping that up now. I might get to include most of that on this video. But the point is, the minimal picture here, the geometry, the cosmological model we'll hold in our head about what reality is, it's a decomposition structure made up of different actions that are balancing the minimal possible universe. The minimal thing that projects out to a sphere has to have an internal boundary, and those internal division boundaries have to have a certain shape. The minimal possible shape on the inside that they could be resting on, all the way in the inside. You can have many transforms of shape, but if you go to the bottom level, because it's a quantized set, a non-infinite radius, right? It's also going to be quantized in a number of steps. So at the bottom level, that step has to be balanced on a geometry of some sort. And if that's the minimal possible closed manifold, then we're talking about the simplest possible way to form a projection on the outside, a universe that decomposes and maintains its own boundaries. And the logic structure of that decomposition, the way things break up into different pieces and fit together, defines all the rules in physics and chemistry, defines all the connective equations of physics, literally the equations, the algebra. It also defines the quaternion construction of reality. This four-dimensional decomposition is quaternion by definition, right? Clifford algebra is captured in that picture. The structure of the field that we're doing mathematical operations on in general, that discovery of that field in mathematics is the same thing we're discovering in physics. The geometry that's responsible for the actions of physics is the same field, the same structure of decomposition inside the minimal possible maintained stage, self-maintained, right? It's the same thing. So that decompositional logic is mathematics.
Well, that was one of the big things that came up before when you're like, all right, based upon this construction right here, we can basically derive the fundamental theorem of calculus. Because that fundamental theory of calculus seems to also be used to dissect.
Yeah. Calculus, its big insight is what? That we can get past not knowing. We have a big problem with graphs. Graphs are the way we pictorially represent the relationship between two different things, two different dimensions, right? That's why they're different axes. And you can think of it as a general representation of a dimension, so we'll just call it X and call it Y, or you can label it time and space or whatever, right? But the problem is, once you have a graph, you've got some sort of interesting graph that shows up and has interesting features to it, you might want to be able to ask specific questions of it, right? You look at it and you realize, oh, it turns out there's a minimal point here, first of all. I should be able to ask, what is that? There's, at this point, locally a maximal point. I should be able to ask that somehow, but how do you ask what that point is from the function that you had? Right? How do you find out, say, from this minimal to this local maximum, if I drop a line down here and say how much area is underneath that part of the curve down to the axis? Or you could change, I'm interested in 2 above the axis or 2 below, whatever. There's all kinds of questions you could ask a graph. And a graph is literally your representation of the relationship between those two dimensions. So it's the way you're understanding how those two things fit together, right? So you want to be able to ask more questions. Fundamentally, if you want to know what the dimensions of reality are doing, how they're making reality, how the ingredients at the base of everything are doing the job they're doing, then you have to learn how to understand relationships. This is a relationship of 2. There's 2 dimensions, right? And the graph is telling you what the relationship is as those parameters between them change. Great. So there's properties built into the graph, like areas underneath the curve, right? Slopes at a certain point, all kinds of things. And he noticed that, or Newton and Leibniz and others, but Newton's the main figure usually in the story. He went home during the plague, something we might be able to be familiar with now. And, went through the eye of boredom, we might think today. Instead of spending the entire time watching TV trying to pass the time by, he literally focused and focused and focused on one conversation, trying to understand how to understand relationships better. Okay? And to do that, he realized, well, I might not know how to just get an answer for the area underneath the curve, but I do know how to get something close. This is a huge insight, especially when it comes with the ability to then get closer and closer and closer, right? So he looks at this and says, well, I can stripe this thing up, right, into a whole bunch of shapes that I do know. I don't know how to get the area of that shape, but I do know rectangles. But the problem with rectangles, of course, is that you're not going to be getting the exact area, but you are getting to get a close area, right? And how do you get closer? Make the rectangular smaller, right? So he came up with a conceptual way of seeing the world that allowed you to stripe things up, use the equation for striping things up to get an area, but then make the stripes smaller and smaller and smaller and find what the limiting approach to an area is. And now voila, you have the ability to calculate the area between any 2 points. Magic, right? I mean, magic, insight. Imagine no one had thought of that before. So they were stuck at, oh, area under the curve? Well, your guess is as good as mine. He looked at it longer and realized, oh, I don't know how to get an area of that shape specifically, or if I change it from here to here, it's a different shape now. Right? I don't know how to do that specifically, but I do know how to do something else. The key feature I want you to focus on is that this striping things up and then getting smaller and smaller and smaller, what happens when you go to 0? Now you're dividing things by 0, right? Lots of times. An infinite number of times. So he comes up with the concept of an infinitesimal, a thing that acts like a 0 in all ways, except you can divide by it. Okay? He defined it as smaller than all other numbers, but bigger than 0. It's confusing. It's not a very clear insight. It's not as clear as what this was doing, right? But it's noticing that you have to have something at the bottom, right? And so I'm going to say let's don't treat it as a 0. Let's just say it's really, 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 really small. Like 10 to the negative 8, 10 to the negative 18, or 10 to the negative 32. That's really small, but it's not 0. And then the stripes, therefore, won't go to 0. They're going to go to small, skinny stripes that have an exact value, right? It means you're quantizing the world and then counting up the number of things you did that way, versus quantizing the world a different way. See, this is striping X in little slots like that, but you might be striping Y this way in a different scale. Now you get so many X per Y natural divisions. But this way of breaking things up into stripes is a way of quantizing the subject, quantizing the graph, right? And here we're quantizing a universe into existence. Before that, there were no universe properties. There was nothing. There was no speed of light. There was no communication. There was no people. There wasn't anything when it was just infinite chaos. The smallest, simplest possible structure that you can impose on chaos is this one, the hyperbolic figure 8 knot, being its minimal internal volume complement, the thing that it's resting on as it wraps around at the very inside, and hypersphere of maximal volume on the outside. It's all connected as one piece of parts moving around, and on different scales, it looks like bigger pieces moving slower, doing different things as you until you get to the outside.